So just as a show of hands, how many of you know anything about GPUs? OK, so a few of you. OK. Well, before we get into that, I'd like to start with a tangent. Now, this beautiful red vehicle here is an MGB GT. It was produced roughly in the late 60s, and I'll tell you the truth, I've always really wanted to buy one. Because apart from the fact that British cars are kind of rare these days, it also has this particular benefit in that if it broke down, I could probably fix it. Right? I could probably, if I was on the side of the motorway and the very ancient engine inside passed out, I could probably wrangle myself together and fix it. And that's something I can't really say for a car like this. So this is a very modern Volvo. And I'll be honest with you, I don't have a clue how this works in any way. Right? This could die, and I would be stuck there, and I would need a mechanic to come and fix it. And chances are they would just tow it somewhere else. And the reason why I bring this up is because actually, if you look at these two vehicles, the ways in which we interact with them really haven't changed that much. So this car, of course, has lots of clever internals, so it'll have sat-nav and radio and things like that. But actually, from the perspective of driving, it's just, you're just changing gears, you're moving your foot pedals, you're steering. Not much has really changed. And I really want you to keep that idea in your head, because that's going to be something that comes up again and again throughout this talk. Now, I'm going to embarrass myself a little bit here, which is I recently started a new job around about 6 months ago. And you can imagine, right, first day, kind of a little bit nervous. Join a first call, and they say to me, Joe, we need you to make this program faster. And these words, for me, are simultaneously very exciting and also terrifying. Because you've joined a company where you care about the people who work there, you think they're good, and you've joined and they've said to you, we have no idea why this is slow, and we hope you might be able to help us. And what made this even more scary is I knew nothing about GPUs when I started this job. In fact, for me, the idea of CUDA reminded me of this Barracuda. And I was petrified equally at both, right? Because I knew nothing. I didn't know anything about how this works. I had no idea, much like Thomas said, on how to make this thing faster than it already was. And so, much like any good person, I go on YouTube, I try to find a tutorial, and I end up writing a program that looks something like this. So this is essentially a variant of C called CUDA-C. And you can see that we've just got essentially a regular function here that is essentially memset, right? So we take a pointer and we just overwrite it with this value val. And so down here, when the first time I tried to run it, I just allocated 100 ints, passed them to the GPU, and expected it to do something. And something really weird about this program is it sometimes works and sometimes doesn't. And whether it works or not depends on both your hardware and your software. And I found this absolutely astounding. This was so weird, the fact that this seemingly very innocuous program would sometimes work and other times just not. And so the question for our talk today are two things. Is one, why does this sometimes work? And two, why was our otherwise performed program slow? Now these two programs are not really the same, but they have enough similarities to overlap. So with that, I just very briefly want to dive into the differences between a CPU and a GPU. So when you're writing code for a CPU, you normally have many threads that run, and you have to make them concurrent in an explicit fashion. So if you're writing, say, pthreads, or you're using the C++ standard library, you have to explicitly say, I want this thing to be parallel. With GPUs, it's kind of similar, but actually a lot of the concurrency that you have is implicit. So you're very declarative when you write your code, and you say, actually, when this actually eventually runs, I want to take this portion of the thing and do some work on it. And really, by form of analogy, I want to talk to you about the differences. A CPU is kind of like an office, right? You have lots of people who are working there. They're all doing kind of relatively independent tasks. They have their own space. They're doing their own things. But actually, they're kind of doing roughly kind of general stuff. Whereas a GPU is a little bit more like a factory. So in a factory, you have really specialized equipment for particular things. You can make tables or cars or whatever. But normally, factories don't make many different things. They just make one thing very well. And you can see here that we have all of this storage space. I actually don't know what this factory is for, but this storage space down here contains all of the raw materials. And for the purpose of an analogy, you can think about that as being our memory. Right? We've got things here that have arisen from somewhere, and we're going to use that somehow to do some work. This analogy does stretch further. So if you think about an office, you have sort of dedicated space for each person. Here, you might have multiple different teams that do certain things that all share the same workspace. And you schedule these teams in and out based on essentially what needs to be done on that particular day. So just to capture this in some, I guess, a more programmatic way, this is what I mean by the implicit concurrency. So here we've got the same function as before, which is essentially memset, but what we're doing now is we're saying that each thread that runs is going to process 32 elements, or most 32 elements. And then we're going to split this range from the pointer into essentially sub-ranges that are indexed by low and high. And then with this check here, make sure that we don't overwrite anything. But fundamentally, this is how we get our concurrency, right? We specify a very small program that just divides up our range, and we expect that this will run in parallel. Now, you'll forgive me for going off on so many tangents, but I think this one is important. Does anyone know what this car is? Okay, I don't expect you to. It's utterly unimportant in its own way. So this is the Ford Model N. And I know nothing about this car, other than the fact that it came before the Model T. And the Model T was the first car that was built using a moving assembly line. So before the moving assembly line was invented, the way that you would build a car is you would have a fixed position, and workers would move around and work on it iteratively. And Henry Ford one day had a dream where he was like, what if the pieces move and the workers stayed fixed, rather than the pieces staying fixed and the workers moving? And this was really a massive revolution at the time. And it led to this thing here, which is called the moving assembly line. So where the people are fixed and the things keep moving. And the thing I want you to take away from this is that we're really going to prefer the moving assembly line when we can. Really, we're going to prefer a setting where we can get the hardware to do very particular tasks in a way that there's no dependency between each other, right? Each bit only has one particular thing that it must do. And one of the ways that we're going to encapsulate that is via this notion of a stream. So a stream is an ordered sequence of events. You can push tasks into it, and you can expect and guarantee that they will run in some sort of consistent way. And the reason why we do this, by the way, is because sometimes there are tasks that will be waiting for certain things. So for example, on a GPU, you might have a task that spends most of its time reading and writing from memory. And that's a really inefficient use of the hardware a lot of the time, because that's kind of slow, and your computation will be very fast. And so you want a way of telling the computer, oh, hey, you can do something else here. That's fine. And you do this via the notion of a stream. And this will come up later. So you can see here, this is, again, another code example. This CUDA stream underscore T type is just this type in CUDA that says, this is a logically consistent set of operations. Please execute these particular tasks on that stream. And you can see that with these angle brackets here. This is a sweeping generalization. I'll make several of these in this talk. The idea here is that GPUs thrive in settings where the computation to data ratio is really high. So if we go back to our factory analogy from before, you can imagine a world in which the workers of the factory really are just waiting for raw resources all the time. They're very quick, they're very good at doing their job, but they're waiting a lot for the raw resources to arrive from somewhere else. And if that shipping time is too long, then maybe they will spend most of their time idle. And to give you sort of the canonical example of this is matrix multiplication. So in matrix multiplication, you typically, if you have an n by n matrix, it takes O to the n cubed time and O to the n squared data. And this is one of these situations in which you get a real speed up by using GPUs. Now, you'll hear this a lot in performance tracks. I really don't like the big O notation here because it kind of lies. So there are asymptotically better algorithms for matrix multiplications that are not faster on GPUs. And that is in part because actually your constants really do matter in these settings. Now with all that said, we're going to write something. We're going to write a memcopy function that can handle any type of copy efficiently. And by this I mean if I pass it memory that is in CPU, I want it to be able to transfer that memory quickly. If I pass it memory that's on a GPU, I want it to be able to copy that quickly. I don't care, I just want it to be able to do it efficiently. Now, conveniently, anyone who's written any code will know memcopy exists. CUDA, in fact, has functions for this. So really, it might just seem that all we've got to do is pick, in each case, what it is we're going to do. So just to conceptualize that slightly, there's 3 different types of memory that we need to worry about on a GPU for the purpose of this talk. The first one is stuff that comes out of CUDA malloc. Now this is, as the name suggests, it takes your memory on your graphics card and it outputs it gives you some buffer that you can store things in, right? It's like a regular malloc replacement, but just on the GPU. Now, this memory is really special because it's constantly prioritized. So it will never migrate. It will always be in that memory. It will stick there forever, and you can't change that behavior. You would have to manually decide that you wanted to move it somewhere else. This is obviously different from a regular allocator like malloc, which can move the memory around as it sees fit. The second one of these here, which we also won't worry about for the purpose of this talk, is CUDA malloc, where you essentially allocate memory in system RAM, and then you make that accessible to the devices via memory mapping. The reason why you'd want to do this is because it means that your graphics card can access system memory directly, which is super cool. And by the way, if I just used this, the first bug that we had wouldn't have been a bug. But for the sake of this, again, we're going to ignore that. And I just really want to focus on this last one here today, which is managed memory or unified memory. Now, in this case, what happens is you're allocating memory where the physical storage may be either on a hardware device, so a GPU, or in system memory. And what's funny about this is it's kind of ethereal to an extent, because it's not always in one or the other. In fact, you can end up with a situation where, much like the stars in the sky, it's somehow in the ether. Right? It moves between the two depending on what it is that you want or the pattern that you're expressing to the program. I just want to very quickly go over how they achieve this lovely magic. So you'll hear lots of performance tricks from all of us today, but one of them is if you don't know what's going on, use strace, because it really can tell you things that are going on that you otherwise didn't know. So in this case here, I wrote a simple program that just used CUDA malloc managed to give us some memory, and I ran it through strace. Now, the very first thing that it does is it opens a file descriptor for this special device here, which is something that NVIDIA provide. That essentially is an interface between your system memory and the device memory. And then here, we're just going to allocate a large slab of memory via mmap. Those of you who are very familiar with binary will know that that number there is 64 megabytes exactly. So you can't customize this. It will just immediately say, please give me 64 megabytes straight away. And then after that, it deallocates some memory. Like it deallocates 32 megabytes. I don't know why. I've not been able to find anything written down that says why it would deallocate these 32 megabytes. It just does it. But then finally after that, it takes the memory that it gave you before, adjusts it to your alignment, and then gives you back the size that you wanted. And that's what this result value here is. Now, you'll notice that the mmap is different between this line here and this line here. And the reason why is because here we're specifying where the memory should exist. And the important part of this is that actually this is how we ensure that the pointers are the same across both the system and the device. Right? We're specifying and saying, oh, this thing should absolutely be at this address, and we should use that file descriptor that we open up here for that address. So really, we're specifying and saying, this is where this should live. And then when you deallocate, it's very, very simple. We just remap the memory that we had before and then free what's left over. And this is really what's going on under the hood, is every time you do this, you're making a series of system calls, you're mapping your memory into different places, and then it's eventually getting rid of it. OK, so now we know all of this. I just want to show you what happens in the profiler when you do this. Now, this is NVIDIA's system profiler, by the way. It's a super useful tool. They're not paying me to say this, but I would promote it if they did. It's really, really very useful. So here you can see essentially the program that I wrote, which we previously ran through strace. So down here on the left, you can see that we've got that malloc managed call, which essentially says we're going to allocate this memory. Fill is the mset function that we had before. And you'll see that when that actually runs, which is that blue line at the top there, we immediately have a page fault. The reason why this happens is because the way that the driver actually enforces this etherealness is when you allocate the memory to begin with, it doesn't assign it physical storage. It just gives you an opaque page. And then when you actually run this, the very first time that it faults, it's going to go, oh, I need to allocate some physical storage for this. I've had a page fault. And so this long bar here is it actually allocating that memory on the device and handling the page fault. And you can see from this bar, maybe it's not so clear at a distance, that actually most of the time of this very small function running, is just handling the page fault. In some settings, this won't be true, but you can certainly imagine a world in which this ends up taking a great deal of your time. And in fact, if you allocate even more memory, you actually get a very similar pattern that has some nice quirks. So first of all, you'll see that we do get this repeated page fault on writes, but actually the spacing between them is kind of irregular. And the reason why is because each time you have a page fault like this, the hardware tries to help you, and it tries to allocate more memory each time. And that's why you get this very somewhat irregular pattern where the first time we don't help much, then the second time the hardware helps more, third time it helps even more, and so on. And this is, interestingly, if you expanded this line the whole way out, you would see that this entire pattern actually repeats. And the reason why is because after this last one here, we have an even larger gap between faults. And I don't quite know why this happens, but once this does happen, the hardware seems to forget that this is a problem that you're running into, and so it stops helping you as much. So you'll actually see that this pattern that repeats will eventually continue to tile itself the entire way along. I think the programming guide for CUDA says it best, which is that the physical location of the data is invisible to a program and may be changed at any time, even if that's obvious to you or not. So at any point, no matter what you're doing, the underlying physical storage of that memory that you're accessing via that shared pointer can change. And I think this is it's worth thinking about this for a second because it's not very often that this happens, right? It happens a lot with programs, right? We saw Julia's talk earlier where processes can move, but it's actually very rare that memory moves like this in a way that is entirely opaque and in a way that matters this much, right? It happens sometimes with caches, sure, but that's kind of different to this because the difference there is that actually you're just making a copy of something, right? You're just storing something and then you're dealing with it. But here, your entire program's data can just move if you do it via this pointer. This is the second half of this quote, which is that access to the data's virtual address will remain valid and coherent from any processor, regardless of the locality. And actually, I think this is actually the only way they would be able to do this, because you've got so much going on, you've got so many processes that are running. But I think that this is actually the really very interesting part of this talk, is that the accesses must remain valid. And that's going to have a lot of very interesting implications for the performance of our program. So I've told you all of this, and I have told you that functions already exist for CUDA copying. So all we need to do, right, is all we need to use memcopy. I mean, if we've got a managed pointer on the left and a managed pointer on the right, this should be super fast, right? And it should work, because this will run on the CPU, the pointers are accessible via the CPU, it's going to work great. Everything's going to run fast, right? No, we have fallen into the pit. This is our eponymous pitfall. And you can really see this from this graph here. So you'll see that as we increase the size in gigabytes, which is the x-axis, and the the gigabytes per second on the y-axis, you'll see that we're jumping around a lot, right? A huge amount. In fact, to begin with, when we're copying a gigabyte, we're getting just over 600 megabytes per second of throughput. And by the time we've gotten the whole way up to 70 gigabytes per second, we're only getting, what, 0.85? Now, I don't know how often you benchmark your memory bandwidth, but that's dreadful. That's really, really bad. I could write to and from an SSD and get faster than this. And the reason why this happens is because of some clever stuff. So I'm now going to break out the profiler for a second. Again, this is the NVIDIA System Profiler. And if I open this notice, here we go. So if I zoom into this, bear me a second. The keyboard shortcuts don't work on macOS. This is the first time I'm trying it. OK, so you'll see here that we end up getting CPU page faults. So I just want to recap. So previously, we had the memory on the GPU. We've just done something. And now we're trying to do a memcopy on the CPU. And you'll see here that we have a page fault. And this page fault is where the GPU or the CPU tries to do a copy, and it realizes that it can't access the page. And in fact, as we zoom the entire way along, although maybe I need to zoom out with it, you'll see that we get loads of these. We get all of them the entire way along here, over and over and over and over and over again. In fact, in this particular trace, there's something like 37,000 or so. It's tremendously awful quite how much of our time is just spent with these page faults. And there's an interesting interaction here between the device, the graphics card, and the CPU, which is that actually we're limited here by the page size of our CPU. So if we think about the anatomy of a page fault, what happens? The first thing is that the CPU is going through memory, and it goes, oh, I haven't got this. I'm going to need to request it. So it allocates some space, it contacts the GPU, and it says, hey, I need this much memory. And the GPU gives it back. And that amount of memory, by definition, can only be the page size of your system. And here, all of these lines that we see, although admittedly here they're so contiguous that you can't really see them, they're all 4 kilobyte page faults. And something I didn't do, which I probably should have done, is I didn't check how this changes if you increase the page size. I would guess that you would still get the same result as this, but it would be less horrendous. It would probably be slightly better. And that's because each time we have one of these problems, we end up with a syscall because we have to deal with the page fault, and it's very, very expensive to go through this and to get an answer out that is actually useful. So this is captured again here. You can see that we end up with all of these page faults over this span, which is really, it's not great for our performance. This is the same thing but zoomed in because I just want to show some causality for you. So as we zoom really, really far in here, you can see that we end up with this regular repeating pattern of page faults. And once again, something that's interesting is these patterns repeat and they're equally spaced. Oh, sorry, they're unequally spaced. You can see for these two here, we have a very small gap, and then a slightly larger gap, and a slightly larger gap, and a slightly larger gap, and that this pattern repeats. And the reason for this, I'm not sure if you can all see, but you have these purple blocks here, followed by the red blocks. And this is the hardware trying to help you. This is the hardware trying to give you more than you've asked for. So each of these red lines are a page fault for 4K, and then the purple lines are a speculative prefetch. So it realizes, oh, I've had this page fault, that's really bad, I'm going to transfer over more memory. And as before, you can see that the width of each of these blocks grows the more times you fault. So by the time you get here, I think it's something like 2 gigabytes it transfers back over, say. But right at the bottom, it's only, I think, 64 kilobytes. So each time you make this mistake, it tries to give you more memory to make things faster. This is all handled in the hardware, by the way. You don't need to do anything. It's just done by the device directly. But Joe, I hear you say, you've already told me these functions exist, right? We have CUDA memcopy to copy between things. Why are you writing your own memcopy? And sure enough, actually, it does give you some better results if you use it. So this purple line down here is if we use managed memory, but we specify that we're copying from the device back to the CPU. And this is just only ever so slightly faster than what we had before, and you'll see that we still end up with this sort of relatively stepwise curve, and this is just because it can handle the prefetches more efficiently. Meanwhile, if we go the other way around, so we go from the device back to the host, you can see that we end up with this very fast line, right? We get up to about 10 gigabytes per second coming back. And this is just because of the pages, again. So it turns out that the GPU actually has more capacity for dealing with larger pages, up to 2 megabytes. And that's really what you see here. You end up with this nice curve that gives you something that is slightly better. But it's still not great, right? 10 gigabytes per second of transfer is still not incredible. And so just to summarize this, if you're writing code that needs to deal with this generically, I highly recommend that you don't use standard functions and you just prefer the CUDA functions. So here you can see that even in the slowest case, which is this purple line here, we're roughly twice as fast as on this slide here. And that is just a one-line change. I didn't do anything else. The operation that's happening under the hood is still the same. And in situations where you can get more of a speed up, like this green line here, you'll see that actually it's still worth it, right, just to do this generically. But of course, all of this begs a question, which is that all of this cost has come from the fact that we're handling page faults. We're handling the fact that our physical memory isn't mapped to the place where we're doing the work. And so a question that you might have is, well, what if we just move them to the same place to begin with? Right? What if, as opposed to doing the copy between GPU and CPU, we just moved the memory to the right location and we did the copy there? And so conveniently, CUDA lets you do this. I'm really not a fan of this prefetch term because it's not really a prefetch, it's a migration. But all this does is it says, I'm going to ask you, please, to move the memory that is backed under this pointer to the destination device. And you can put it on a stream if you want, force it to take to be consistent with some previous operations or to wait until some previous operations are finished. But I do just want to point out that you do need to specify the size. And this actually gives you a really clever trick, which is that you can, if you want to, only force some of the pages to be in any one given place. So with this, you can actually end up with an array that's split across multiple devices, across the CPU and the GPU. You can split it however you want. And that actually gives you a different sort of parallelism in a way, because if for whatever reason you wanted to, you could do an update on an array on the GPU and on the CPU at the same time. And it would all work fine because of the guarantees that they give you. So if we do this, and we do the prefetch just on the source, so if we're copying from one vector to from one pointer to another, and we just move the source pointer to the device, you can see that we get a much nicer curve still. Right? You can see that it increases here, it flatlines at about 16 gigabytes per second, which is kind of okay, and then it drops right like a stone. Now, the reason for this actually depends on your device. So all of the numbers in this talk were gathered on a H100, and a H100 has 80 gigabytes of memory. And so you can see that whilst both our prefetched and our destination array can fit in memory, everything goes fine. And then right at the point here, when they can no longer both fit, our performance tanks. And this, again, just happens because we're now in the realm of getting many, many page faults again. Right? We're encountering these page faults. We're going to end up with a situation where we're trying to write to something or trying to read something that we don't already have. And so our memory just completely flatlines. And this is even more pronounced if we try to prefetch them both. So if we try to prefetch both of the pointers ahead of time, which is what you can see here, you'll see that we get a huge amount of performance. Right? This is 1,300 gigabytes per second. It's huge. It's so fast because we're doing a copy between the memory on the GPU and the memory that is also on the GPU. And this works really, really well right up until we get to the point where neither or both pointers don't fit in memory anymore, and then our memory bandwidth just completely crashes. Right? I think this is something like 600 times slower, this line here, because what we've done here is we've actually given up the ability to be able to proactively manage this. Right? We've essentially said, we're just going to let you deal with it, and then we're going to get the poor performance we had before. And this is a very visual representation of what that looks like. So you can see here that we have all of these red blocks of doom, as it were, and you can see that they're mostly surrounding read requests. So we're trying to read some memory, and we don't have it, and so we transfer it from the host to the device. And then this second line here is us saying, oh no, we're out of memory. We have to get rid of something back into system memory so that we can read more stuff in. And you'll see that this continuously happens. And I'll be honest with you, the system's not that clever at deciding what it should get rid of and what it shouldn't. I've seen this before where it's really, really screwed up and really, really given us very poor performance because it's evicted things that we haven't even used yet. And so we're constantly reading things from memory that actually we really would rather not have to keep rereading. And you can see that here with these continued page faults for reads and for writes. So our second conclusion is that we need to manage these copies more carefully. Right? We can't let the hardware deal with it for us. We've got to somehow do better by ourselves. And so the solution to this is we're going to want to end up with a profile that looks something a little bit more like this. Now, this is actually a trace from a running program that we had internally at Poolside. This was actually the problem that I was sent to diagnose. And you can see here that we've got kind of these memory accesses here, but by the time we get to this bit, it just completely crashes. Right? Our bandwidth goes horrendously. We're constantly just faulting. And you can see that with these spikes on the PCI Express bandwidth numbers up here. You can see that we just spike. We just end up consuming more and more. By the way, so I know that on this chart here, it sort of went down at 40 gigabytes. But actually, you can see this graph under any circumstances if your device memory is full. So if you use the CUDA malloc API from before and your device memory is really full, remember, it will never get evicted. And so you can arbitrarily move where this graph sits to the left by just allocating more card memory. So I think in our case, it was something like we were moving 512 megabytes repeatedly, and it was causing this unbelievably slow bandwidth because it was constantly trying to evict things it needed to work on. It's actually very easy to trigger this behavior. So what we need to do here is we need to manage these copies more carefully. And I'm very quickly going to show you how to do that. So the first thing we're going to do is we're going to define this prefetch size here. Now this corresponds to roughly 2 megabytes of data that we're reading. And I'm going to make 2 streams, which are S1 and S2. Now, these streams are important because it's going to enable us to queue our operations properly. And then, of course, here I'm just going to calculate the number of prefetches that we need. And this is the magic of the loop. So what we're going to do is we're going to start doing this copy. And the very first time, we're going to prefetch the previous thing that we had, and we're going to send it back to the CPU. So that's what this CPU device ID thing means here. So we've done some operation, we've taken some data, and we're going to send the bit that we had before, and we're going to push that back to CPU memory. And again, we have to do this explicitly because otherwise our performance is just going to tank, but also because the CPU needs to be involved with remapping things back into its own memory. Right? You can't just unilaterally do it. You need to give it that information back, and it needs to be involved in that. And so the way that we say this is we go, oh, okay, well, we're going to queue those on a particular stream, and we're going to explicitly send them back to the CPU. The next thing we're going to do is we're going to prefetch the blocks that we need from system memory back onto the card. So this device ID thing here is just a placeholder that says this is the ID of the device that we're sending the stuff to. And you'll notice that we use a different stream here. Now, you could do this on the same stream. You could use S1 for this as well. But actually, in practice, it doesn't really make it much better. It is better to do it like this because your GPU is already doing things. Like, it's kind of useful to have it know that it's got things that it's got to do stuff on. I think I'm missing a slide. But anyway, if you do this and you unroll the entire thing, you end up with this line at the bottom here. So you can see that unlike our previous graph, which we had back here, where we had lots and lots of these not very nice red lines, by the time we get to here, the red lines have all but disappeared. In fact, there's this tiny, tiny one here, but that's a bug that I've still not worked out what it is, so we're going to ignore that for the sake of this. And you can see that just by combining these variously clever prefetches and sending things back to where they were before and managing them, everything gets much better. In fact, I don't have the hard numbers in the slides, but at least from what I've done impromptu, this actually beats most of the standard CUDA functions for doing this. If you write your own custom code and you're careful about dealing with this and you can track how much memory you've allocated, this will beat all of the standard library CUDA functions, at least on the hardware that I have access to, under the drivers that I have access to, you know, all the usual caveats, right? Now, with all of that said, I want to return to this MGB here. You'll notice we've blitzed through a lot of stuff, right? We've gone through a lot of hardware stuff. And I find it so astounding that originally when we were talking about this, we were like, oh, this single pointer is going to make our lives so much simpler, right? Just having one pointer that we can use across both devices and across system memory, it's going to make our lives great, right? Everything's going to be so much easier. And in a way, it kind of reminds me of the upgrade from this car to the Volvo, right? We've designed stuff and we've put stuff into the world under the mantra of it being simple. But actually, I don't think that's really true, right? I mean, we're on slide 51, and I spent all of this time explaining this stuff to you around something that should have been simple. And it's just not. It's actually very complicated. At this point, I think I'd rather just manage the copies myself. And I think it really comes down to the fact that, much like this car, we're programming for a computer that was designed 50 years ago, right? We're programming for a PDP-11. We're using the same stuff that we've always done. And actually, we've actively resisted change. Because for those of you who are at least in some retro computing, we had this discussion with near and far pointers in the 90s. Right? We had this idea of changing the language so that we could express the hardware more explicitly, and we just haven't. We've actively tried to stop ourselves from changing the tools that we use to meet the hardware that we're running on. And I want to highlight this point home. It is impossible to statically determine if this function works or if this code works. Right? The compiler can't tell you. Assuming that these functions are public, you can't know, because you have no way of expressing succinctly that this pointer here that is passed in is something on which you can operate. And trust me, this will not blow up your computer or anything. Like, everything will work fine. There's no memory violations here. The hardware is clever enough. But it strikes me as so weird that you can't just say, by the way, this thing needs to be this, and expect it to work safely in any meaningful sense. We've resisted all of this change, and it's really not been that good. So I want to give you some takeaways before the end here. So the very first thing I want you to do is I want you to profile your code. And in particular, I want you to profile your code. Right? I want you to use different tools. I want you to try clever and innovative things like strace. I want you to really try to understand why things are happening the way they're happening, because although computers are confusing, there is almost always a reason. It might be a cosmic ray, it might be something crazy, it might be something that none of us understand, but fundamentally there is always a reason for this. I want you to consider where you can simplify things, and I don't mean this in the sense of simplify like, I've rewritten this loop or something like that. I mean, when someone reads your code for the first time, do you have to give them an hour presentation before they know why it's doing what it's doing? That's probably not that simple, even if it looks it. But above all, I really want you to choose performance, and by that I mean, if in doubt, performance is good. And with all of that said, I'd like to say thank you very much, and make sure you vote and leave feedback. Thank you. Yeah, sure.
I have a short question. I mean, so where does that mechanism of that shared memory or of that architecture comes from? If in the end you tell us it's easier or it makes more sense to do it ourselves?
So NVIDIA and AMD both sell it as an easier way to get your program started. So if you've got an old legacy CPU application and you want to port it to a GPU and you want to start early in a way that you can sort of be aware when things are breaking, you should use unified memory. And actually, it does make your life easier in some ways. It's just, if you're trying to use it in an environment where performance really matters, I don't think it's worth it.
So it's for migration reasons or backwards compatibility?
Exactly, but you will see some people using it for other reasons. So for example, if you need more memory than you can fit in your GPU, so let's say your working set is 100 gigs and your device memory is 80, it is useful to sometimes have this, but actually I don't ever think it's better than just doing it by yourself. And in fact, in the end, that was exactly what we ended up doing, right? We ended up doing the copies by hand because it just wasn't performant enough for us. And it was too hard to predict as well.
Okay, thanks.
No worries.
Was the overhead that you saw in your mem copies always page fault related? Like if you were copying twice from device to host, would
no,
the second copy be fast?
Actually, it wasn't. So I will open this profile for you here. And you'll see here that our occupancy, so the amount that our device is being used, is actually really very high. What happens here is, it goes back to the coherency thing that I said before. So when you're dealing with memory in any way, the actual device hardware needs to make sure that its view of the memory is consistent everywhere. So even if you're just requesting that same page across multiple places on the same device, it will store. So actually, just counting the number of page faults is not enough. There's certain tricks you can do when you're writing your code to make sure that actually each page that you're reading is only needed in one place. But it doesn't really overcome the issues.